Oh, by the way, my phone fell off, so I actually have to record that part again, but I will continue. I was talking about energy levels in hydrogen level in harmonic oscillator. So you have to get to the end part is that you have to move from this part to this part, and every part you have to put computation for every other part as well. So it actually grows exponentially very badly. So this is very computational, and it takes a lot of energy, and you actually don't have any idea about the maximum level of maximum energy level here. So this is very vague idea. So we cross this part, and then we came along with another idea where we have a finite energy level, and you know that after this energy level, you can actually get to the ionization level, and you have an idea here, right here. So when you go from this part to this part, you actually computed energy level. You compute the energy level for other. But when you're trying to reach this part, there is a very small amount of energy shift here, very small amount of difference from this part to this part, and to compute to move from this part to this part, you have to apply energy in a very precise and accurate way, and it actually it turns out to be 1/2 power n accuracy. So as soon as the energy level increases, the accuracy level increases sharply, which is really bad when you're trying to compute in a precision. So your precision is going to be get dumped off when you're going to apply this part when you have ionization level, and you know the ionization level, and you know the part where it can actually get out of the shell, and you can get the resultant factor. So this is a really bad idea, and we don't actually use this part, which actually makes sense that why are we using this type of computation format. So this is why we are using Qubit. You actually have to perform n operations when you are moving from this part to this part, because for every both of these conditions, you know that it exists in 1 or 0. That's it. So you know that this is 1, you move apart, and you have to, for example, you have to go to the part where it is 4. So this is where the 4 is, and you know the state here is 1. To move at this part, you actually have to move 4 times. That's it. It's nothing like this, which is really not fascinating, and which is really hectic and takes a lot of energy. That's why we prefer this one, and this is why we are using qubits, because qubits only have truth states 0 or 1, and for meantime the condition or the condition of the qubit is either 1 or 0 in format or in a circuit. So it's very easy to compute by moving linearly in operations. But here you have to move from this energy level to this energy level. You have to go through all energy level, and to move from every energy level, you have to put energy in a harmonic oscillator. Consider this like a hydrogen atom with infinite energy levels, and they are not energy levels but they are infinite because we don't have any spectrum for that, and this is why we have to put a lot of energy to take that part. For every part you have to go again and again from every other part. So this is very computational, and this is also very resource taking, and it also destroys the precision. So when you are moving from this part to this part, and when you are between these parts, you actually have to apply a lot of precision to get to the correct one, and the precision level is 1/2 power n. So which is very small and very dangerous when you are in the computation world, because this is very small precision level. It's I think if you have 20, if you have 100, if you have 1000 as n, it will go into 00000 and so on, or whatever. I think it will be a lot, which is really difficult to compute the precision at the level. That's why we use this one. Next we are going to discuss. Next we are going to discuss about the single bit interference of qubits. This is something about the gates, and we will get the idea how the gates are actually implying the interference, and we will be using only one single bit qubit system, not a multi-bit qubit system, which I defined in the previous video, where we had a multi-bit qubit system like this, and they were connected, and then we have another result. But we we are actually using a single bit Qubit system to define interference pattern using gates. And then after that we will come along with the velocity, and after that we will talk about other gates, Pauli exclusive gates and Clifford gates, XYZ gates, which are also part of their family, and then we will continue with the next part, entanglement. Thank you so much, and I think that's it. I will record the lecture the other day.